Hi, I'm Kaori Ikematsu from RI Corporation. This work has collaborated with Kunihiro Kato, Hiromi Nakamura, Hinako Suzaki, and Yuki Igarashi. I'll be presenting the paper FoodSkin, Fabricating Edible Gold Leaf Circuit on Food Surfaces. In this work, we investigate an approach for adding interactive elements to food by implementing edible gold leaf circuits. Augmented foods integrated with edible circuits can provide interactive eating experiences. In the field of human-food interaction, researchers have explored various techniques to enhance eating experience by using food as a part of the circuit. For example, they have explored techniques for providing auditory feedback or presenting electrical taste sensations while eating. However, these techniques have been limited because they are only applicable to food with high moisture content, capable of conducting electricity. With their low conductivity, dry foods prove challenging in adopting these techniques, thereby restricting design possibilities. Researchers have also developed techniques to integrate dry foods into circuit by using edible gold leaf. For example, edge sensor provides sensing capability using the gold leaf electrodes pasted on the food. However, the fragility of gold leaf makes it challenging to create circuit of arbitrary shapes. Another technique involves using a laser cutter to create arbitrary patterns with gold leaf. However, this technique is limited to food with melting properties like chocolate, as the food needs to melt when transferring the gold leaf patterns. To overcome these limitations, we propose FoodSkin to create gold leaf traces of arbitrary shapes of various dry food surfaces. FoodSkin does not significantly alter the original taste and flavor because we used tasteless and odorless materials. This enables the integration of various displaying and sensing functionalities on dry foods. So let me describe the fabrication workflow. It starts with designing gold leaf traces by using design support system. First, user select food and interactive elements from the preset menu. Then, the user specifies area where the interactive elements will be applied to a 3D model. The system displays preview traces on interactive elements to fit the specified area. Users can freely manipulate traces to be applied. During this process, a warning message is displayed if the user drags a trace over areas with captures that do not allow the placement of traces. Users can also edit the shape of trace. This example shows editing the connectors for resistive heat. As the user adjusts the connector's placement, causing the trace length to change, the system automatically adjusts the line width to maintain the consistent resistance value for the trace. The warning messages are displayed if design error occurs, such as short circuit or line width are too thin. Once editing is complete, the fabrication file is generated as a PDF. The next step is fabrication. Gold leaf is thin and fragile, making it difficult to process in its original state. Therefore, we initially reinforce the gold leaf by using wafer paper. We put wafer paper onto the gold leaf and stick them together by rubbing the surface with a soft material. Then we use a laser cutter to process the gold leaf. We use a fabrication file from the design support system for this process. During the cutting, there is a possibility that the wafer paper may partially melt and adhere to the cutting bed, potentially damaging the gold leaf when it is removed. To avoid this, we first create hollows corresponding to the trace patterns on the two layered wax-coated papers. We then sandwich the gold leaf between the wax-coated papers. This reduces adhesion to the cutting bed. Finally, we apply a solution of starch dissolved in water as an adhesive layer onto the surface of food. Then place the gold leaf traces on it. Once the adhesive layer is dry, The gold leaf trace function as electrodes or wires.
Next, we show several applications of our technique. In this example, the chocolate has electrodes capable of direct contact with the tongue, allowing for the presentation of the multi-point electrical stimuli in oral cavity. This enables the simultaneous presentation of the electrical taste sensations at multiple arbitrary points. By creating a comb-shaped pattern, we can integrate a resistive heating element into food. For example, by embedding a resistive heater in a chocolate cake, we can keep a chocolate inside warm and molten. The resistive heating element can also be used to enhance the olfactory experience by facilitating the evaporation of volatile compounds inherent in the food. Edible circuits are also useful for sensing eating behavior. It shows a nutrition bar integrated with the resistive sensing elements. As the user takes a bite, a portion of the traces is damaged, causing an increase in resistance. The system measures the user's eating speed by monitoring a change in the resistance value. In this example, the candy incorporates a capacitive sensing element to detect contact with the tongue. When contact is established, an external speaker emits audio to enhance the interactive eating experience. Next, I'm going to present the result of 3 types of evaluations. First, we conducted the technical evaluations to assess the applicability of the proposed technique and the durability of the gold leaf traces. We evaluated the durability of the traces when stretched. We applied gold leaf traces to 3D printed geometries to stretch it. To account for differences in the strength of the wafer paper used to reinforce the gold leaf, we prepared gold leaf traces with 3 different thicknesses of wafer paper applied. We found that the traces could not withstand stretching to length of 5% and had low tensile durability. When the length of stretching increased, we observed cracks appearing on the gold leaf, resulting in an observed tendency of increased resistance. We also confirmed that thicker wafer paper leads to less damage from the stretching. Then we investigated the applicability of the proposed technique for surfaces with varying roughness. We prepared 7 different Greek sizes of sandpaper and adhered 3 thicknesses of traces to each. For traces with thinner wafer paper, an increase in surface roughness resulted in higher resistance. However, for grid size of 100 and above, we observed that the resistance remained largely unchanged. On the other hand, for traces with thicker wafer paper, we did not observe significant variations in resistance across all grid sizes. This suggests that the thicker wafer paper adheres to the sandpaper surface in such a way as to fill in the bump on the sandpaper surface, thereby reducing the effect of the bump on the gold leaf. We then assessed the applicability by adhering traces to various foods with different surface properties. For this experiment, we selected 9 foods with low moisture content. We created a total of 12 traces patterns consisting the 3 thicknesses and 4 line widths, and adhered each traces each of the food. Firstly, we confirmed that all traces exhibit good adhesion to the 9 foods. We also found that conductivity remains stable in thicker traces. Nevertheless, employing thin traces or adhering them to uneven food surfaces could harm the gold leaf and increase its resistance. Next, we conducted a psychophysical experiment to assess the impact of our technique on taste and texture. In this experiment, participants first memorized the taste and texture of both processed and unprocessed foods. They were then blindfolded and randomly presented with either processed or unprocessed food. They then consumed the food and were asked to answer whether it was processed or unprocessed. This graph illustrates the accuracy of the user responses in each condition. The closer the accuracy is to 50%, the more difficult it was to distinguish between processed and unprocessed items, suggesting that processed foods are close to the original taste and texture. We found that thin traces shows accuracy close to 50% in both taste and texture compared to thick traces. Considering chance rate of 50%, the overall accuracy is not particularly high. Therefore, we can say that the proposed technique of food processing does not significantly affect the original taste and texture of the food, regardless of the thickness of the trace used. To evaluate the usability of the proposed technique, we conducted a workshop with local students as participants. This workshop consisted of 2 sessions. In session 1, participants performed a task in which they adhere pre-prepared traces to food items. In session 2, participants were provided with examples of traces and were tasked with creating traces similar to the examples. Participants went through a series of fabrication processes, including design using a design support system, cutting out traces with laser cutter, and adhering them to the food. During the workshop, all participants were able to complete tasks within predetermined timeframes. Additionally, participants could use our design support system without the need for special training. On the other hand, it is assumed that some practice may be necessary to adhere food without damaging the trace. Next, we will move on to discussion and limitations. In applying the proposed technique, it is necessary to connect external devices such as power supplies and microcontrollers to traces of the food. However, connecting such devices directly to food with wires is not desirable. Therefore, we investigated the implementation of electrodes using gold leaf on plates or packages. This implementation, although simple, is expected to be readily accepted by users due to its hygiene and ease of use. Furthermore, based on the results of the technical evaluations, we confirmed that the durability of the tracing stretchability is not particularly high. Therefore, there may be difficulties applying the technique to cookies or muffin batter where the shape changes when baked. This is conclusion. Thank you for listening.